minus alpha is their absolute difference is less than like 10 raised to power minus 100. So it means this approximation solution x is very close to the your exact root alpha. So how we get these solution we will learn in this numerical method course. So basic needs in the numerical method, it can be computed in a reasonable amount of time. Like today we have lots of computer and computing facility, and we use these facility to get fast solutions instead of searching the exact solution, because sometimes we don't know the how to obtain the exact solution. Times if we know how to obtain the exact solution, but that one is a very like a time consuming process. So instead of that we go for approximate solution by using some numerical algorithms. So for example, you know that this is a okay, you know that okay, this you know this is your second order equation in the variable x, and you know its solution can be obtained by using this formula. And this formula you are using from your like 8th standard, and you know that the solutions are x equals to minus 1 and x equals to minus 3. Instead of this, if I am having this equation like x raised to power x raised to power 9 minus 2x square plus 5 equals to 0. So how to get the solution of this? Maybe some analytical technique is available, but we don't know yet. Maybe someone in future will discover some analytical technique and through which we can get the solution. But till now we have to find a algorithm or procedure so that we can get some approximate value of x, so that if we substitute that value of x in this equation, x raised to power 9 minus 2x square plus 5, then we get some value near to 0. Instead of 0 we will get like 0.1 into 10 raised to power minus 100. So it is somewhat equivalent to 0. Similarly, this is our another equation, x equals to e raised to power minus x, and we want to know how to get the solution of this equation. And till now we don't know how to solve this equation analytically, so we will solve this using some numerical techniques, and we learn how to develop the numerical technique and how to apply these numerical techniques to get the solution of these kind of problems. Now we have this system of equation. Most of you, almost all of you know that this is a two equation in two variable x1 and x2, and you know how to solve them. Like we substitute one variable like x1 from using equation 1 into equation 2, and then we will get easily our solution like x equals to 2 and x1 equals to 1. So this is the procedure. We know that if we substitute one variable in another equation from using first equation, and then we'll easily get the solutions like x1 and x2. So if instead of two equations, we have three equations. Three equations, I can say like x1 plus x2 plus x3 equals to 3, and x1 plus 2x2 plus 2x3 equals to 5. So you know that the procedure will take a little more time if we are going to solve the three linear equation in three variables. But if you have thousands equation in thousand unknown variables, so is here you know the analytical procedure. like we take substitute one value and then we'll do. But if we have 1,000 equation and 1,000 variable, that it's take very huge time, and it is not possible to solve using your hand calculations. So for that kind of procedure, so that we have to develop some numerical algorithm so that we can get a fast solution, not exact solution, but fast solution which satisfies this equation with some error. Like I get the value of x1 and x2 such that x1, if I substitute those values like x1 equals to alpha and x2 equals to beta, then the sum of two values is equals to like 3.0000 something. So it is like we are try to get a fast solution in terms of approximate solutions. Okay. Now you can see here in the first integration, the integration of this part is very easy. Like x is x square by 2, and then you substitute the upper limit and the lower limit. And after substituting, you will get this is the solution 4. But instead of this, if I have having this one, so we know that there is no analytical solution to this kind of problems like 0 to a e raised to power minus x square dx. So how to get the approximate values of these kind of integrations? So we will develop some numerical algorithm to get the approximate solution. Even though this one is also looks like easy, like e raised to power minus x square, but instead of that, if I am having like e raised to power minus x square plus sine square and then divided by some log x, then it is more complicated. And maybe there some analytical solution exists in future, but till now we don't have any analytical solutions. But in some engineering problems we have these kind of situations and we want their solutions. So instead of exact solution, this numerical method techniques will provide you the approximate solution. So we'll learn all these techniques in the later classes. Now, like maybe in your third semester, you have learned or maybe in second, you have learned your how to solve a differential equation, and there you learn like linear differential equations with the constant coefficients, and some of the differential equation in which we have like a non-linear equations, but in some limited number of cases. Like you know that if the differential equation is of this particular type, then only you are able to solve or able to find their analytical solutions. So like this kind of problem you have already dealt in your second or third semester, and here dot y dot it is representing the differentiation with respect to x, and y double dot is like a second time, two times differentiations of y with respect to x with these two initial conditions. So this differential equation you can solve. But instead of this linear differential equation with constant coefficient, if we have non-linear differential equations, and instead of this second order, if we have third order, fourth order or 10th order differential equations, and we know that there are very, even though you know this in your third semester, that we are not able to solve all kind of ordinary differential equation by using the techniques you learn in your third and second semesters. So there are many differential equations which are of non-linear kind of nature, and you are not able to solve, and their even though their analytical solutions are not yet developed. So for that kind of differential equations, we have some numerical procedures or numerical algorithms so that we can solve any ordinary differential equation by using our numerical method techniques. But the compromise is here is this: we will get the approximate solution instead of exact solutions. Similarly, we can solve the partial differential equations like if you have more than two independent variable like this. So this solution can be obtained for this kind of partial differential equation. I don't know whether you learned this solution of partial differential equation in your second or third semester. But this can be solved, but there are more complicated situations of partial differential equation that cannot be solved using our analytical methods. So we learn this also, how to solve all partial differential equation using our numerical methods techniques. But the compromise is the approximate solution. This, as you are a computer science student, so I think all of you know this. Number systems, like in decimal number systems we represent any number like this, and then this is the how to store in the computer, like we have some bit to store sign, some bit to store this integral part, and then some bit we require to solve this fractional part also. So this is the normalized, like if we use this some bit to store exponents and some bit to store this mantisha and some bit to store this sign also. So this is normalized floating point representations. Then binary system, you also know this is binary system, base 2 digits 0 and 1, and this is the way we represent any like binary number. So here also, like this is a one binary number 1.101 with base 2, and we know how to convert any binary number into decimal number by using this procedure, and the equivalent decimal number is like this 1.625. So there are situations, like you can see these situations. If you have one decimal number 1.1, and this is in base 10, and now you want to convert this you want to obtain the equivalent binary number to this 1.1. So if you try to obtain this binary number corresponding to this number, you will get this kind of infinite expansion. So it means you are not getting exact binary equivalent to the this decimal number 1.1. So it means we have to truncate somewhere to write this 1.1 in decimal to its equivalent binary. Like you can truncate here, or you can take 100 digits after this decimal points and then you truncate, but you have to truncate because this process goes indefinitely up to infinitely. So it means we have to do some approximations. Then this is like a 32-bit systems and 64-bit systems, and this is the way we store number in 32-bit system, like 1 for sign, 8 bits for exponent, and 23 bits represent fraction. Similarly, in double precision system, we have this process. Now you can see, suppose I want to calculate this 3.578 into 2.139, and you know that if my computer is if my calculator is having only 2-digit accuracy, so it means that the result is this one, 3.57 into 2.13 is equivalent to this 7.60. But you know that if you exactly multiply this, you will get this one. So you see that this is the true answer, but if our computer or calculating facility is limited, we will get this kind of approximations, and we will use this kind of approximation in our calculation if we don't have the facility. And you know that the computing facility till now is limited, so still you have to, because no one is going to calculate till infinite, so somewhere you have to truncate the infinite process, and then approximations starts. Then we have the accuracy and precision. Accuracy is related to the closeness of the true value, and the precision is related to the closeness to the other estimated values. So we'll see this. So here you can see in the A diagram, suppose your root is in the middle of this circle here, and you have some approximated roots. These black dots are approximated roots. So you can see like in what we do actually in a numerical algorithm, we randomly select some initial guess for any problem. Like I say a very simple problem I will take. I haven't taken one equation like x minus 2 equals to 0. So x minus 2 equals to 0 equation has root x equals to 2. But I want to solve this equation by using some numerical technique. So to do this, what I do, I assume some like x1 or say x naught. X naught is equals to 1.59. So 1.59 is not exactly equals to 2. So what I do, I use this x naught equals to 1.59 and use one method, and then I get x1 from this x naught, and the x1 is like 1.599. Then I will use this x1 to get x2, and the x2 is 1.5999. And then I use this x2 to get x3 like 1.5999. So this is the way we'll get the approximated like sequence, approximated root sequence to the actual root 2. So none of them is equivalent to 2, but they are moving towards 2 as our number of iterations are increasing. So here like we are getting different suppose this is my x naught, then I will get x1, then x2, then x3, x4, like this I am getting. So after the using a sequence of approximate solution, I am getting this. Okay. So here I am getting this kind of solution using our approximate method. Then we are going to this increasing in the right to right, we are going to increase accuracy. So here we can see that our approximating sequence of roots are actually going towards the exact root. But here you can see the approximating roots are themselves making some neighborhood, and they are closing in the neighborhood. Like if I increase whatever I get x1, x2, xn up to infinity, they all go inside of this rectangle, this selected rectangle. So it means they are not going towards the exact roots. So there are this kind of situations are also there. So it means the approximated root themselves accurating themselves, so it will increasing the accuracy precisions. Like 2 consecutive, like x10 minus x9 is like 10 raised to power minus 5. Then x11 minus x10 is equals to 10 raised to power minus 6. So this is the way we are increasing the precision, but they are not increasing in terms of the accuracy. But if increasing this precision and accuracy increases, then we will get this kind of results, and we are actually getting the our not still we are getting the approximate root, but that is actually close to our exact root. So this is the way we define our accuracy and precision. Then we have this error. Okay, one thing I want to say here, like here you can see that none of the sequence of the approximated root are going to our exact root, because exact root we are assuming inside this circle. So none of them is going. So there are like methods that fails to produce the exact root. So this is the drawback of the numerical techniques. Like we have selected one numerical procedure, and then we have selected some initial root x naught, and on the basis of that numerical procedure we have obtained x1, x2, xn, and they are not going towards the root. So what we have to do, either we have to select change our x naught, or we have to change the method to get the root. So now we define this absolute true error, like true value, that is the true value means is the exact value to the problem, and this is the approximated value. So this is the way we define our absolute true error. Then absolute percent relative error is defined by this: true value minus approximation divided by true value into 100. So this is the way we calculate absolute true value or in the true error and absolute percent relative error. Then we have estimated error. So how are defining this estimated, like current estimate and the previous estimate. So in true error we are using the true value, but in estimated absolute error we are using the current estimate, like we are here in the x11, then this is the x11 and this is the x10. So this is the way we obtain like estimated the absolute error, and this is absolute estimated absolute percent relative error, like current estimate minus previous estimate divided by current estimate into 100. And this, like if we want to fix this, like because if we have started one numerical procedure to get the some approximate root xn for some exact root like alpha, then xn minus alpha, that is error, and that should be less than some 10 raised to power minus 10. If it is less than 10 raised to power minus 10, then for that particular xn we stop our numerical procedure. Because like if we are calculating from x1, we are getting x1 from x2, sorry, we are getting x1 from x0, and then x2 from x1, then x3 from x2, and like this we are going. So we can go till infinity. So we will stop somewhere by giving some fixed criteria that I will stop my repetition of iterations if my error is less than 10 raised to power minus 10 or 10 raised to power minus 20, whatever it is fixed by you or your systems, and then you stop. That I have to stop here. Then we are having this another procedures like Taylor series expansions. Though this we are discussing here because we are going to use this Taylor series to prove some numerical methods, to drive some numerical methods. So you have to recall this. This is the Taylor series expansion of the function fx about the point A, and it is defined by this fa plus f dash a, and this actually this infinite expression is equivalent to fx if this expression is converges, and if this does not converges, then this is not equivalent to fx. So we have obtained Taylor series expansion of the function fx about the point A, and this is the denoted by this. You have learned this in I think it is in first semester, Taylor series and Maclaurin series. And this is in their summation form. Summation k equals to 0 to infinity 1 upon k factorial f k bracket remains k times derivative at the point A and x minus a raised to power k. So if this highlighted series converges, then we say that this is equals to fx. Then we have Maclaurin series. So you know that in Maclaurin series, instead of the like in Taylor series we are expanding the function about some point A, but in Maclaurin we are expanding about the point origin, that is a equals to 0, and the similar thing is here. If this infinite series converges, then it is equivalent to fx, and this one is known as Maclaurin series. Then here is some examples like fx equals to e raised to power x, and then you know that fx is if equals to e raised to power x, then obviously f0 is 1, f dash x is again e raised to power x, then it is again 1. Then f double dash of x is again e raised to power x, and f double dash at 0 is again 1, and similarly fk0 is 1. So this is the our uh, Maclaurin series expansion to the function e raised to power fx, and we know that this series converges if absolute of x is less than infinity. So this is actually representing the radius of the convergence of this infinite series. Like this is infinite series, I think you have already learned in your first semester itself, and there you learned this is the infinite series and their convergence domains also. So this is the radius of convergence. So for this kind of series, the radius of convergence is infinity. And here we have taken term by term, like we if we because we are if when we go into numerical approximation, we are not going to use this infinite series or to store this infinite series in some system, or even though we are not able to write this infinite series in some notebook. So if I want to use some approximation of ex, so it depend on our requirement. Like if I require less accuracy, then I truncate my series here. Like I neglect this selected expansion and I approximate e raised to the power x by 1 plus x. Instead of if I require much more accuracy, then I truncate the part that coming in this rectangular region, and I assume that e raised to power x equals to 1 plus x square upon 2 factorial plus x cube upon 3 factorial, and use this as our in our calculation. So here you can see if I approximate e raised to power x by 1, that is first term, then I will get this is the straight line. But if I use two terms, first two terms 1 and plus x, then I will get this green curve. And if I use three terms like 1 plus x square by 2 to approximate ex, e raised to power x, I will get this red curve. But and if I use the plot this e raised to power itself, then I will get this curve. So you can see that if I'm using only three first terms, then I'm getting the Bechdel approximation to the e raised to power x. Even more Bechdel approximation, the fourth term is enough. So it depends on your calculation requirements that where you have to truncate this series. Similarly for sin x also, and in the similar way you can calculate the their Maclaurin series. The Maclaurin series for sin x is this one. So here again the radius of convergence is infinity, and here we will use term by term. We'll see, like if we use less number of term, like only first term, then we'll get this one. And if we use only two terms, then x minus x cubed by 3 factorial. If we use three terms, we are getting near close to this red curve. Curve is corresponding to the sin x. Then cos x. Then this. So then you can see this is another series function fx. And if you use your Maclaurin series method, and you will get this kind of series. And here you know that this series is converges only when your domain is absolute of x is less than 1. So in this domain, if your x is lying in this domain from -1 to +1, then only you can use this as a approximation of 1 upon 1 minus x. So we'll see how we'll check these. Can we apply for the series for x greater than equal to 1, and how many terms are needed to get a good approximations? This we will see in the Taylor's theorem. Again we have fx equals to 1 upon x at a equals to 1, and this is the expansion. Taylor's series expansion is 1 minus x minus 1, x minus 1 whole square, like this. Now we have another function fx equals to log x, and we have to calculate its Taylor series using the point A. Earlier in Maclaurin series we are using a equals to 0, but here we are using a equals to 1, and we are getting this is kind of Taylor's expansion for log x about the point A equals to 1. The Taylor series converges. The Taylor series converges fast when x is near to the point of the expansion. So if x minus a is large, then more terms are needed to get the good approximations. So if your this difference is large, then you require more number of terms in the infinite expansion or Taylor series expansion of the. So this is also like a remainder form of the Taylor series theorem, and this is also this already learned by you in your first semester itself. Like this is like we are here, we have n terms expansion, and then this we are taking as remainder, that is the error, and this is like this. Rn equals to fn plus 1 derivative at xi upon n plus 1 factorial x minus a raised to power n plus 1, and xi is between a and x. So this is the way we have taken like fx is approximated by first n plus 1 terms. So what is the error? So the error is given by this. So here like fx equals to 1 upon 1 minus x with the point of expansion equals to 0. So we know that x, if because if we use x equal to 0, it means we are getting Maclaurin series, and we know that for fx equals to 1 upon 1 minus x, the domain of convergence is absolute of x less than 1. So if x equals to 1, then the function and its derivative are not defined, and the Taylor is not applicable here. So we try to get this is the error. We know that in our Taylor theorem. So what is the maximum error? Because for if we take this as error, and we take n plus 1 terms, then what is the maximum error? So we'll try to get the maximum error bound for this from this expression. So to get the maximum error, like for example, we have taken this fx equals to e raised to power x, and we have obtained its Taylor series expansion about the point 0. So instead of Taylor, we can say Maclaurin also, and we have taken first 4 terms, that is n equals to 3. So this is your fnx, because it is e raised to power x. It's all order derivatives are equivalent to e raised to power x, and we have taken x raised to power xi. What is the value of fn xi? Because this fn xi is required here, because when we are trying to get the error bound, in the error bound we have this xi, you can see here. Here also this xi, and the condition on xi is the xi is lies between a and x. So xi is greater than a and less than x. So to get the error bound, we require this value of this fn xi. So how to calculate this one? We know that fnx is equivalent to this one. Here a is 0 and x is 0.2. And xi is lies between a and x. So if fnx equals to e raised to power x, so if xi is between a and this x, it means fn xi cannot exceed e raised to power 0.2, because the maximum value the xi can take is 0.2. So for any value of xi lie between a equal to 0 and x equals to 0.2, its value cannot exceed e raised to power 0.2 for all n greater than equal to 1. So it means this is bounded by e raised to power 0.2. And what about this? Here x is 0.2 and a is 0. So it is like 0.2 raised to power n plus 1. And after simplification, you will get this one. So like if you have used n equals to 3, that is 4 term you have taken in the from the Taylor series expansion of e raised to power x, then the maximum error you will get is this one. Here we have put a n equals to 3. So this is the way, that is, this is the maximum error between the exact value and the approximated value. What I mean by this, like if you directly obtained f to 0.2 from this, or you obtained f 0.2 by using its Taylor series expansion using first 4 terms. And this is another form of this. And this is also required when we are like when we learn polynomial approximations. So this we will see, like instead of, you can see here also, here we have x, this is our x. Instead of x, I replace x by x plus h. So if x is replaced by x plus h, then you will get this kind of approximation, f equals to fx, because now a is your x and this is step size h, because the earlier your first point is a and another point is x, and their difference is x minus a. But here first point is a, that means x, and the next point is x plus h, and their difference, that is x minus a earlier, is now x plus h minus x, it means h. So this is this x minus a in the previous expansion is replaced by this h raised to power k. So this you have to remember. This is another form of the uh, Taylor's theorem, like this. Here this is the Taylor's theorem about the point x equals to a, and here we have replaced a by x and small x in the above x plus h, and we will get this another form. And you have to remember this form actually. Both of them is required, but this is mostly used when we are going to drive our formulae for the polynomial interpolations. And then this one is, so suppose we have fx equals to e raised to power 2x plus 1, and this is the center of expansion is a equals to 0.5. Then how large can be the error when n plus 1 terms are used to approximate e raised to power 2x plus 1 at the point A? So here x is actually, we have to calculate the value at the point x equals to 1, and we have to obtain the Taylor series expansion about the point a is equals to 0.5. So to get this, we know this is our fx, and its first derivative is 2 raised to power e raised to power 2x, second derivative is 4 e raised to power 2x plus 1, and like this we get kth derivative of kx equals to 2 raised to power k e raised to, hello, e raised to power 2x plus 1, and then we have obtained their values at the point 0.5, because we want to expand fx equals to e raised to power 2x plus 1 at the point a equals to 0.5. So we have these values. After substituting these values, we will get these kind of Taylor's expansions. And then we have written all the terms here. Now we calculate the value, the error, because error is represented by this. If you remember the remainder form of the error, it is actually f n plus 1 time derivative at the point xi, where xi lies between a and x, upon n plus 1 factorial into x minus a. Here a is 0 0.5 raised to power n plus 1. So we have substituted all the values, because here we have already calculated fkx is equals to 2 raised to power k e raised to power 2x plus 1. So it means fn plus 1 xi is like 2 raised to power n plus 1 and e raised to power 2 xi plus 1, and x is 1 because we are calculating the value at x equals to 1. So this is there, and then this can be rewritten as like this: 2 raised to power n plus 1, because 2 raised to power n plus 1 is a positive number, so this came out of this absolute. And this again 1 minus 0 0.5, so here 0 0.5 again a positive number, so this is also come out of this, and factorial also positive, so it is also come out this. So we have this e raised to power 2 xi plus 1 maximum, where because we know that the xi is like between 0 0.5 to 1. So if we replace this xi by 1, we will get the maximum value of e raised to power 2 xi plus 1. So we replace here xi by 1 to get the maximum value, and this is the maximum error in the Fn. If you have taken like n terms, like n plus 1 terms, if you have taken n plus 1 terms to approximate the value of F1 when this is expanded about the point 0 0.5. So this is the maximum error. So these are the basics required for this course, and for tomorrow we will start like this one, this solution of nonlinear equations, and we will discuss this topic from, and we'll first learn bisection method, and in this method we will learn how to obtain the roots of the equation, like if we have this kind of equations, how we get the approximate roots. Today I stop here, and tomorrow we will start from the first topic, like this bisection method. Like first topic is solution of nonlinear equations, even though we learn more like the solution of nonlinear equation and transcendental equations also, like algebraic algebraic equation, this ones, x cube minus 4x minus 9, and then there's some transcendental equations also, and we will develop these methods, like if we have this kind of situation, how we'll get the root. So we'll these transcendental equations also, and where to stop. So all this we'll discuss tomorrow. So if you have any question, you can ask. And since today is the first class, so today I am going to give attendance to all of you. One more thing I want to clarify: the timetable for your class is 10 to 11, Wednesday, Thursday, Friday. Is it?
Sir, 9 to 10.
It's 9 to 10.
It's 9 to 10. But they have given. Are you sure it's 9 to 10? Hello?
Yes, sir. Yes, sir. It's 9 to 10.
So you have another class from 10 to 11?
Yes, sir.
Okay, then I will take, you inform others, even most of them of you are here, around 41 students are here. So tomorrow I will start class from 9, okay? Because whatever timetable I received, in that it is 10 to 11. So tomorrow I will start this class from 9. Okay, and you inform to others also. And today I'm giving attendance to all of you, and start like practicing this course from first class itself, because like within 10 or 15 days I will take the test. Okay. So if there is no question, then it's better to leave. I'm also leaving.